In this example, we're going to look at the mutual inductance parameter between two coils. We're going to examine in more detail how we're going to problem solve when we're given actual values and numbers to deal with, and we're being asked to look at the induced effect in one coil due to the other coil. So let's see what we have here, because it can be a little difficult at times to see exactly what direction to go in your analysis. So let's see what we're looking at. We have a transformer, we're told, is built with a 1 meter solenoid with a cross-sectional area A equals 2 centimeters squared. We are told we have a primary winding, script n, sub 1 times 10 to the 5 turns per meter. So they're identifying clearly for us, it's a lot of turns, 1 times 10 to the 5, right? That this is going to be coil 1, the big one. So this is our N1 coil 1, and N2 is only 5 turns, so clearly they've given us 5 turns for N2. And that is the first thing you absolutely want to do in your analysis. If they don't label them for you 1 and 2, you immediately label coil 1, coil 2, and the next thing you do is you find out which coil is the driven coil, which coil has the power source that is putting current through it. And in this case, it is coil 2. So coil 2, we are being told, is connected to a power source. So it has a current being driven through it that is changing as a function of time. It'll generate a changing flux, which will give us an induced effect in coil 1 in this case. Okay. So the first thing we are asked to do is to solve or calculate an equation for the mutual inductance of the two windings. Now, there are always two approaches to take, because the mutual inductance is reciprocal, right? It's an action-reaction effect. It'll be the same value for the two-coil system. So you will always be able to look at, 2 is my red one, so let's take a look at what we have here. So you can always take coil 2, flux 2, and set it equal to our M parameter times current 1. Current 1 is the current that makes the B field, the changing B field, in coil 2, if that's what we're looking at. The other option, of course, is to take coil 1 times the flux generated in coil 1 and set that equal to the mutual inductance constant times current 2. Current 2 generates the changing flux in 1, which makes the induced voltage. Well, here we've chosen equation 1, the first version. So let's see why that worked in this case. So it really doesn't matter which you choose first. If 1 works, that's fine. If it doesn't, you just go to the other. Those are your only options in terms of the equations relating to mutual inductance of the two coils. So I put the 2 in here, but we can drop it. Okay, so the 2 is just referring to the N2 flux 2, right? But it's really a 2-1. So here I'm using this first equation, and that's down here. So that first equation here is this one here. So we're solving it for M, N2 flux 2 divided by I1. Now, the flux through coil 2 is generated by the current in coil 1, and we don't know the current in coil 1, but you'll see in a moment that's going to cancel out. We don't need to know it. But the flux through coil 2 is going to be generated in a mutual inductance setting by the B field made from coil 1 times the current, and please add the subscript in there, the current, times the area associated with coil 2. So the flux through 2 has to be associated with the area 2. But the B field through 2 can be coming from coil 1 if coil 1 has current in it. Well, the B field for the solenoid 1 is given by mu naught script n I. Now we see our i's cancel out. We were given the number of turns per unit length of 1. We were not given the number of turns of length of coil 2. And the fact that coil 2 was our driven coil doesn't matter for the mutual inductive constant because it's a constant. It's like L. Let's take a look at what makes a large mutual inductive constant. Right? What makes a large constant is a large number of turns of one of the coils, in this case coil 2, a large number of turns per unit length of the accompanying coil, and a large cross-sectional area, and now they share the same cross-sectional area. That will not always be the case, so I'm going to put a subscript 2 in here, so please add that to your note page here. Well, in this case, we were given everything we need. We know the number of turns of coil 2 is 5. Mu naught is a constant, 4 pi times 10 to the minus 7. The number of turns per unit length of 1 we were given, 1 times 10 to the 5. And the cross-sectional area, of course, is the same for both. And we do have to be a little careful with our units for cross-sectional area numerically here because we were given centimeters squared, and we have to make sure we convert that to meters squared. Okay, so it's the same for both coils. Now, had we set up the equation the other way, it would have been fine, except we didn't know N1 and then the script 2. So it's okay if you choose the wrong one of these equations to start with. It's not a matter of wrong, but if it's not the one that you're given the parameters for in the problem, that's okay. Well, now we're all set. Since we were given the time rate of change of the current in coil 2, we can calculate the induced effect in coil 1 because now we know our mutual inductive constant M, and we know the time rate of change of coil 2. So we just plug it in. We can get our answer down here. And the only thing, I'll leave the algebra for you to look at, but the only thing I would like you to note is that we are not going to include second-order effects unless they explicitly tell us to. So, of course, coil 1 has a self-inductance, right? So we have a self-inductance here. If we can calculate that self-inductance, if they give us enough information to calculate an L1, we could, of course, say that the current I1 is based on Ohm's law, I1, not isobar, I1 times the resistance in coil 1, so I would also be a function of time, and we could calculate that second order effect as well. So as you can see, there's a lot going on in mutual inductance problems. Believe me, we are not going to be intentionally trying to muddy the waters with these problems. If we know our basic equations and we're working within the parameters in the problem, they will be very solvable for us.